Okay, so the first is the integral test. If f is positive, continuous, and decreasing, three conditions must be met for us to do this. Positive, continuous, and decreasing. Then we can turn our series into a function and talk about the integral from 1 to infinity and what the integral does, whether it converges or diverges. Then the series will do the same.
If it was increasing, that means it has to be divergent.
Sorry, I have to think about it.
So it's divergent, it's increasing.
Well, if it's increasing, we can't use the integral test. We have to use something else. I mean, in theory, it's probably going to be a divergent series if that's the case. But if it's an increasing function, we cannot use this test. We would have to use a different one to show divergence. Okay, so you are remembering the derivative test. That is something that we can use to show that a sequence is increasing, or in this case, decreasing. Okay, remember there was 3 ways to show a sequence was decreasing. There was the ratio test, the difference test, and the derivative test. Okay, any one of those you can use to show a function is decreasing. Probably the easiest is going to be the derivative test because we're in calculus. That's what we did all of last year, right? I will say that the book has this written as x is greater than or equal to 1. All right. What it turns out, though, is they're a little bit flexible on whether it's decreasing at the starting point or just after the starting point. Okay, so I write it like this just to show you that there's that flexibility. And I'll show you an example here, my second example. But, what's funny? Okay. But as long as we are decreasing indefinitely, we can use the integral test. Okay, so we're going to do 3 examples with the integral test. And then I'm going to open the door for the one. Okay. Now, an important thing to understand: we do not know what it converges to. All this is going to tell us is if it converges or not. Okay, with geometric, we can find the sum. With telescoping, we can find the sum. But the integral test is only going to tell us if it converges or diverges. That's it.
Is it going to be the only way to find that for some of them?
Yes, and I'll talk here pretty soon about when I think you should use the integral test. Okay. So here's the first one. Go ahead and write it down. If you decide that you want to use the integral test, the first thing you need to do is write it as a function of x. And you need to check 3 conditions. Is this a positive function? Is that always above the x-axis? At least from 1 to infinity. Is it positive? Yes. Is this a continuous function from 1 to infinity? Yes. okay? Then we need to make sure that it is decreasing. And you have to show me proof that it's decreasing, okay? So, like I said, we can use ratio, we can use difference, we can use derivative. I think this is the easiest to use a derivative test for. Huh?
You just like drawings.
No. I'm going to use calculus, okay? Derivative of e to the negative x, negative e to the negative x. Is that less than 0? When? Always, right? Okay. So we have a decreasing function. Okay. All of that just so we can use the integral test. So then what we're going to do, since this goes from 1 to infinity as the sum, then our integral is going to go from 1 to infinity. Okay. Now, if you remember from way back in chapter, was it 7? So, when we have an infinite integral, we have to take the limit, as we'll call it a, approaches infinity, of the integral 1 to a of e to the negative x dx. Antiderivative for e to the negative x. Negative e to the negative x. So we have the limit as a approaches infinity of negative, I'm just going to write this as 1 over e to the a. Is that okay? Instead of e to the negative a. And then minus a negative e to the negative first. I like writing them as fractions so we can evaluate the limit easier, since that's something we have to do. Okay. Towards infinity, what happens to negative 1 over e to the a? The denominator goes to infinity, which means the fraction will go to 0. Okay. So we have 1 over e. Okay. What does that tell us? That this integral converges, right? When we were doing infinite or improper, I guess, improper integrals, we would say, okay, this converges to 1 over e. Okay? All we care about is that this converges. Okay? So since our integral converges, then the sum from 1 to infinity of e to the negative n also converges because of the integral test. The 1 over e really doesn't matter. All the 1 over e is telling us is that that integral converges, so then we can say that our series converges as well. It doesn't converge to 1 over e, we just know that it converges.
Does the number mean anything?
No. Well, I mean, it means that it converges. If we get infinity or negative infinity, it means it diverges. Okay.
It's like anything. Anything that's not infinity or negative infinity and just
Right.
has no relevance to any other topic or concept like what we just found.
Right. It doesn't mean that that's what it converges to. It just means that it converges. Okay. Now, could we have done this one a different way? how I rewrote it. What kind of series is this?
Where did that rate come from?
Geometric, right? What'd you say?
Where did the n come from? Did I write this wrong?
John, you could have made it one, I was just looking at it, I'm like, how is it even the same?
It's just.
What did you say?
Poor Josh doesn't get to see that.
Oh, well, okay, all right, we could have done this and called it a geometric series that converges because the absolute value of r is less than 1.
That would be simple.
Okay, so let's talk about that. Integral test, a lot of work?
Yes.
Okay, integral test is one that you only want to use if you absolutely have to. It's going to be our fallback. Now, right now, since we don't have a lot of tests, we're going to have to use it more than as we go through next week. But it's one of those. It takes quite a bit of work. So if you can do it another way, we wouldn't do it. But for ones like this, we have no choice. Write this one down. So if we're going to use the integral test, let's go ahead and write it as a function of x. And we have to consider three things. Is this a positive function? And really we care about what the domain is. In this case, the domain is 2 to infinity. Okay? Natural log is positive as long as you're plugging in values bigger than 1. X is positive as long as you're plugging in positive values, so we're good there. Continuous. Is this a continuous function from 2 to infinity? Yep. Okay. If we included 0, it would not be continuous, which is why. Or 1 would not be continuous. Nope, just 0. Sorry, just 0. Then we have to think about decreasing. Best way to think about this is the derivative test, especially since there's that natural log there. All right, so our derivative. So the derivative of the numerator is 1 over x times the denominator minus the numerator times the derivative of the denominator over the denominator squared.
You show how you know it's positive or continuous.
No, those should be trivial, right? Okay, so here's our derivative. Is that going to be a negative value? Okay, this is going to be less than 0 as long as x is bigger than e, okay? When x is e, we have 1 minus 1, right? So after e, we're okay. Well, e is like 2.7, blah, 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 right? Now, our integral is going to go from 2 to infinity, right? Now, we're not decreasing until after e, which is like 2.7, but that's okay because, first of all, it's really close to 2. And once we get past e, it's always going to decrease, and that's really what the integral test cares about, is that we're going to decrease indefinitely. So even though our first term we plug in 2, it's not decreasing yet, once we get past e, we're okay. And so the integral test says, we'll give a little leeway, it's fine. All right? Charlie, you don't like that?
Now, is there anything definite, like, at a certain point when you have to say, like, no, we're not using it, or?
It needs to be pretty close to b.
So just subjectively.
The only time you're going to have this issue is you have a natural log.
If you have an infinite number.
Okay. And the only time, like the only examples I've ever worked with have been when it's like, in between if we go to the series, in between like the first and second terms that we like. Okay. So,
What about like a cosine graph? I mean, when you see that it's increasing, you just have to.
it has to decrease indefinitely. Okay. So, we have the integral from 2 to infinity of the natural log of x over x dx, which we then will have to rewrite as the limit as a approaches infinity of the integral of 2 to a natural log of x over x. Okay, here's where we have to remember some of our calculus from last year. How do we do the integral of natural log of x over x? What would we need u to be?
Natural log of x.
Du? That works out nicely, doesn't it? So we have the integral of u du, right? So I'm going to go ahead and take the antiderivative, and we have to switch it back to x, okay? So we have the limit as a approaches infinity. The antiderivative is 1/2 u squared, and so I'm going to go ahead and change this to 1/2 u squared, and we have to evaluate it from 2 to a. So we have the limit as a approaches infinity, 1/2 natural log of a squared minus 1/2 natural log of 2 squared. Natural log of a, what happens towards infinity? It goes to infinity, so natural log squared is really going to go to infinity, right? So this is going to go to infinity. It's not even going to matter what value that is. And what does it mean when we get infinity or negative infinity for our improper integral? Yep. Therefore, the series from n equals 2 to infinity of natural log of n over n.
How may I help you?
Oh, you recognize my voice now, huh? Oh, I said series. That's funny. Okay. What's funny about that is for the past week, since my voice has been like croaky, I'll say hey Siri and it won't recognize my voice. So with the iPhone 7, like you don't have to press a button, you just say like hey Siri, but it gets work. Okay, this was a question. Okay, yeah. So this diverges because of the integral test.
So in class, you just like yell it out and half the people's phones would go ding.
No, you set it to recognize your voice.
Um,
So if I say, hey Siri, it recognizes my voice, but it hasn't listened. So when I'm driving, I say, hey Siri, call Ryan.
you probably remember more than one voice.
I don't know the answer to
So you
that.
can put this one in too.
Okay, questions? Like I said, the integral test is a lot of work, and so it's one of those that is like our last choice almost. Okay, we can do it another way. All right,
You serious?
kind of. Okay, is this a positive function? From 1 to infinity. Is it a continuous function from 1 to infinity? It's not continuous at 0 to infinity. Decreasing. We look at the derivative, negative 3x to the negative fourth is always less than 0. So we have a decreasing function. Which means, hooray, we can use the integral test. Okay. Antiderivative. Antiderivative of x to the negative third.
Negative 2 over x squared.
Almost. I agree with x to the negative 2. Guys have a coefficient in negative 1/2, right? Okay. So we have the limit as a approaches infinity of negative 1 over 2a squared minus negative 1 over 2 1 squared. What happens to negative 1 over 2a squared towards infinity? It goes to 0, which means we actually have a value for our integral. Thus, our series converges. Okay. Luckily, somebody analyzed what happens for 1 over n cubed, and 1 over n to the 4th, and 1 over n to the 5th. And you can see that if I just change that to like 1 over x to the 4th, or 1 over x to the 5th, is it going to go pretty similarly? How about 1 over x squared? Okay. Where we get into trouble is 1 over x, right? Because what's the antiderivative of 1 over x? Natural log. And that towards infinity goes towards infinity, okay? So we can do the integral test every time if we want to, or we can just realize the pattern, and we can use the P series. Okay, so a P series looks like this. Basically, I would copy down right there. That's a P series. The sum from 1 to infinity of 1 over n to the p. P for power. Okay. The series that I showed you Friday as your cliffhanger, 1 over n, that is called the harmonic series. It's a P series where the power is 1. Okay. It's called a harmonic series because 1/2 plus 1/3. Those are some special relationships in music. Okay. Basically, the P series tells us if we can recognize that it's a P series, then we're going to know based on the P for power whether it's going to converge or diverge. Okay. So, as I mentioned over here, I'll come right back. If this was 1 over x to the first power, our antiderivative would be natural log. And then if we look at the limit as a approaches infinity of natural log, that goes to infinity. So to answer your question, your cliffhanger, if P is 1, our series diverges. We don't have to do the integral test. If you have P is 1 for your P series, all you have to say is diverges P series because P is 1. Huh. I'm glad you know.
Scroll up a little bit. Yeah, I didn't look at the whole form.
Okay. Now, okay, we went through a P series where P was 3, and we talked about like 4, 5, 6, 7, 8, all would go very similarly, right? So, if P is greater than 1, we're going to converge. But if P is less than 1, we're going to diverge. Once again, if the P series converges, we don't know what it converges to. We just know that it converges. Okay? This is like the quickest test that we have. This in geometry. Okay? If we recognize that it's a P series, which is a very simple 1 over x to or 1 over n to the power. Very simple. We recognize that it's a P series. We figure out what P is. It's going to converge or diverge. Don't know if you noticed, but how P compares to 1 is backwards for converging and diverging than how R compares to 1. Right? For a convergent P series, we want P to be bigger than 1. Yes?
So what's the use of these tests if you don't know where to converge at? It seems like you're only finding or it seems like you're only saying there is an answer, but I don't know. What good is that?
Well, you'll find more out about that in the second half of our chapter. We have to know how these series work, like whether they converge or diverge, in order to do like Taylor series, Taylor polynomials, all that stuff. Okay, so we're kind of building.
So on their own, they're useless.
Yes and no. I would say they're the big uses. So, 2 examples, and it won't take very long. Go ahead and write this one down. Like I said, these are the best. Okay, is it a P series? 1 over n to the P. It's a P series. How does P compare to 1? P is bigger than 1. So this converges because it's a p-series where p is greater than 1. And you're done. Isn't it? These are the ones you want to look for first on your quiz. Get them out of the way, the easy ones, right? Okay, last example. Write it down. We don't have to multiply anything here, we just have to simplify, right? We have n's in both the numerator and denominator, we can simplify. We can rewrite this as n equals 1 to infinity of 1 over n to the 1/2. Do you agree? Okay, so I'm not always going to give you just a simple, this is a p-series. You may have to simplify something in order to see that it is a p-series. So now we have a p-series where p is less than 1, which means what about our series? Which means it diverges. Also know that, like if this was a 3 right here instead of a 1, we can move that 3 to the outside of the sum and look at the series of 1 over n squared, know that it converges by a p-series, and so then 3 over n squared would also be equal to. All right, so on your goal sheet, you'll find some homework. I can't remember if it's here or not. EOO means every other odd. Okay. So, I think that's the same as. Okay. Tomorrow we're going to have a review day because our quiz is on Thursday.